Hello everyone and welcome back to another episode of OrgoSolver. Today we're going to be going over the hydrohalogenation of alkenes using HBr and HBr with a peroxide. We're going to be using the OrgoSolver reaction solver tool today, so we can find that on orgosolver.com. So let's begin. Alright, so the first thing to start with is going over a little new material here about carbon priority. So we're going to just draw here our pentene, and we're going to make it a methylpentene here. So what we see is that with this carbon, we have a couple of different unique ones. So here in blue are our primary carbons. Okay. Here in magenta, we have our secondary carbons. Let me just get this other primary here. So we have our secondary. And using black, we're going to circle our one tertiary carbon here on the molecule. So, what are primary, tertiary, secondary carbons? So when we're talking about the carbon priority, what we're talking about is how many other carbons are bound to that carbon. So if we look at the blue carbons, they are only bound to one other carbon. These other carbons here that are blue are just CH3 connected to another molecule. Though two in magenta are secondary carbons because they are attached to two other carbons. So you can see there, this one is attached to here and it's attached to here. The tertiary carbon has three other carbon molecules attached to it. So we're going to need that little background information as we start learning about hydrohalogenation. So taking this molecule, this hydrohalogenation works on alkene molecules. So we're going to take our methylpentane and turn it into a methylpentene. So when we're talking about hydrohalogenation, especially with bromine, that's going to be using HBr. So it might be written like this. So let's look into the reaction mechanism for this molecule. So we've got our methylpentene there, and now we've got it here. So when you've got an HBr, if we draw it here with its bonds, remember that bromine is going to have its own lone pairs associated with it. Hydrogens is connected there. The first step in this reaction is the attack here onto the proton with the electrons from this double bond, right? So this double bond is actually just two electrons here. So these electrons come over here and attack the hydrogen, which then breaks this bond and gives the electrons to bromine. And that results in the addition of a hydrogen to the lower priority carbon. So that results in the formation of this molecule, methylpentane, with a positive charge on the tertiary carbon in this example. The next step is that bromine, with its electronegativity, let's see if it shows up here in yellow, now has an extra lone pair. And that makes it really want to attack a positive charge. So this bromine, with one of its lone pairs, will go ahead and attack the positive carbocation on the tertiary carbon. And what that is going to result in, if we go to our tool here, let's look up HBr to find out what it results in. And sure enough, that results in what we had predicted, which is 2-bromo, 2-methyl pentane. So here we can see that all that happened is we took the double bond, we added an H onto this carbon, and a Br onto the tertiary carbon. This is what's called a Markovnikov addition. And you're going to be hearing that word Markovnikov. You're going to be hearing that a lot. And what that means is it follows a rule where the higher priority carbon is the carbon that receives the bromine or the chlorine or whatever functional group is being added on in that reaction. We're also going to go over what an anti-Markovnikov reaction looks like. So for this example, we took our 2-methyl pent-1-ene here. We reacted with HBr, and from here the HBr reacted with the double bond, pulling off the H and sending these electrons to the Br. The free electrons were then free to attack the positive carbocation, forming this molecule here with bromine on the tertiary carbon. When we talked about priorities, what we didn't talk about is what that impact has on the molecule. And a tertiary carbon like this one is better able to handle a positive charge. This one would be the best able to handle a radical or a charge. Secondaries would be the second best, and primaries would be considered the worst. Let's move on to hydrohalogenation using HBr and a peroxide. So this reaction is going to go a little bit differently. We're already going to see the end result here, but let's try and work it out. So in this example, we've got HBr and ROOR. ROOR is just shorthand for any peroxide. And a peroxide is basically a molecule that has this functional group, 2 oxygens right next to each other. These R's could be anything, and just a fun fact, HOOH is hydrogen peroxide, stuff you guys might put on cuts. So in this example, we've got our peroxide, and we're adding it to our methylpentene here. So what ends up happening is that first, the peroxide is exposed to light, and this is the initiation step. So the first step in this mechanism is that peroxide actually splits up here and forms 2 radicals that are identical. So let's just draw the electrons here for completeness. In this example, we have 4 electrons. So you have that molecule plus this molecule. So now that the reaction's been initiated, this is actually the molecule that will start the rest of the reaction. So the next step here that happens is that we take the free radical, and the free radical actually reacts with the HBr. So what happens here is 1 electron goes with the hydrogen, another electron goes with the bromine, and this electron actually binds with this electron here to form ROH plus this free radical bromine here. All right. The next step involves the lone electron from methylpentene reacting with that bromine. So now that we've got it initiated, we're going to do the next step here. Let's rewrite it for some clarity. So we've now got our molecule here and our bromine radical. In a similar reaction that the hydrogen was pulled off of the HBr by the peroxide moiety, here you're going to have 1 electron go to the tertiary carbon, 1 electron is going to pull to that bromine. What that's going to do is going to make that bond, That's going to give you this molecule here. Now this carbon has a free radical. What this free radical is used for is the propagation step, or the next step in the mechanism, where another HBr that's floating around in solution gets activated by that free radical. So this bond breaks, giving 1 electron to the hydrogen and 1 electron to the bromine. This free electron is eventually going to make a bond with this electron here, giving you a hydrogen, which then satisfies this molecule's octet. And now we have the hydrogen that was bound there. We also have the bromine that was bound in an earlier step. And now we have another free radical bromine to carry out the rest of the reaction. This was done in an anti-Markovnikov fashion. And again, just going over Markovnikov and anti-Markovnikov, it sounds complicated, but what it means is which priority did the substrate go to. So here, the bromine went to the primary carbon, and in the other example, it went to the tertiary carbon. So switching back and forth very quickly, we can see that the difference between these two molecules, or these two reactions, is where the bromine is. So here, we see it located on the primary carbon, and here we see it bound to the tertiary carbon. So what do you need to know as far as this reaction and these two reactions go? Again, you're looking for a double bond, and on that double bond, you're going to identify, okay, we have 2 carbons. Which carbon is the higher priority, right? And you find that out by figuring out how many other carbons are bound to it. In this situation, this carbon is a tertiary carbon because there are 1. We can actually number them out here. The blue carbon is a tertiary carbon because it has 1, 2, 3 carbons attached to it. The magenta carbon, right here, is a primary carbon because this is the only other carbon attached to it. So when you're working with a molecule like this, the difference in the reaction is going to be whether it's a Markovnikov addition or an anti-Markovnikov addition. And you can see that it goes back and forth. Well, thanks everyone for tuning in. This was just a short lesson on hydrohalogenation and using the reaction solver tool on orgosolver.com. Be sure to check out our website and practice with more hydrohalogenation reactions, as well as any other organic chemistry reactions that we have listed. Thanks for your time, and I'll be sure to see you guys next time.